will talk about artificial intelligence. But the very good news is that I will not talk at all about math. There will not be any mathematical formulas, which is, these days very hard to find. Whenever someone talks about artificial intelligence, there has to be some math somehow. So the way that species evolved is something that always fascinated biologists and more recently computer scientists. So computer scientists are really getting an interest at the way that species have evolved. And so why? So let's put this right. So why are we here? I mean, I do not mean in that room. We know why we are in that room. But why are we on Earth? Very big questions. Scientists do not have a very clear idea. But there is something that I am very sure about, is that if we are a solution to a problem, then it must be a very complex problem. We have very complex machines, so the problem we are trying to solve somehow has to be extremely complex. And that is the reason why people, especially in artificial intelligence, are having an interest in the way that species evolve in order to solve some very complex problem. So the idea of genetic algorithm is really rooted in the work on natural selection by Charles Darwin. And one of the key aspects here of something like very controversial, but that Charles Darwin says that the strongest they live, whereas the weakest they die. If you have a rabbit, a fast rabbit, then probably it will be able to escape from the wolves and will have therefore chances to reproduce. So this is a tutorial about genetic algorithm. So I hope I won't be too academic. So if I am, please let me know. But I hope I won't be too academic on that. So I will illustrate genetic algorithm. So here we have a new friend, and our friend here think about the word in his head. And then he's challenging us, saying, please find the word I have in my head. So as an indication on, as a way for us to make the search easier, then he would say, for each try you're making, I will tell you the number of correct letters you have. And here we have, another friend here, and she's making she's trying. So, our friends here think about the word cat. So we are not supposed to know about this word. And here we have our friend, she says, cow. And the word cow here has a score of 1, because there is one letter that matches here. Here you have the C here, and you have the C here. So the word cow here has a score of 1. Then you can, then she can make another try, pause. I don't think it is a real English word, but it doesn't matter. And pause here has a score of 0 because there is no matching letters. And here she can try it again with gas, and gas has a score of 1. There is the A here that matches. There is an A here in the second position here, and there is an A in second position. So here has a score of 1. So we can take those, so here we made 3 tries, so we can take the 2 most, interesting tries, which is cow here and gas here. So we can take those words. We have not yet found the secret word. But then we can take those words here and we can start to make some combination of these words. So here we have from gas and cow, we can make go, for example. And go here comes from the G here, this G here, and OW here. And similarly, we can create the word cas. We take this C here and the AZ here. So we are applying some genetic operations. And actually, those are the same genetic operations that happens in our chromosomes. And so we have not yet found the word cat. But we're getting closer, because here we have cas, which has a score of 2, because there is a C and the A that matches. And so we can try, like another iteration here, where we have the GO here and the Z from goes. Or also we can have the cas, in which we will randomly mutate one of the letters, and the Z can be turned into a T. And then here we found the letter cat, the word cat. So this is an example of finding a word in 3 generations. So this is really what genetic algorithm is all about. And so here this is a very simple example, but then later I will show you some more complex, very complex examples. So so genetic algorithm is an algorithm which belongs to the family of evolution algorithm. So the idea of evolution algorithm is, it is very simple. It's very close to what nature has produced. So first we start here with the population. The population can be random or not. I mean, we have a population. What could be an individual in that population could be anything, like literally anything. It could be, some genes, some DNA, or it could be some words, or it could be a configuration for a server, or it could be anything. So from here, this population, we need to select some of the elements. Like we need to promote some elements to be parents. So once here we have some parents, then we enter here the reproduction phase. Some parents, they have the chances to make babies. And here we can then create some offsprings. And hopefully here those offsprings will replace partially or completely the population. And that's the whole idea of evolution algorithm. It's very simple, but incredibly powerful, incredibly powerful. So many evolution algorithms exist. So, for example, here you have the ant colony optimization that is using the same mechanism that the ants are doing, like the pheromone, they're putting that here on the ground, and this is an algorithm that you can use for many problems. Also, there is the artificial immune systems, my wife, she's a biologist, and she explained me once, how the body is reacting against bacteria, and this is impressive stuff. And there exist some algorithms that really reproduce that mechanism here. Also, so many evolution algorithms exist, so I will focus on genetic algorithm. I was thinking at some point to talk about genetic programming, which is fascinating as well, but I will just talk about genetic algorithm. So if we do double click here on genetic algorithm, then this is the whole algorithm. So applied on the word example I showed you previously is really like this. So here we create an initial population made of random 3-letter words. Just create some words. How many words? Here on the example I show you like 3 words, 2 words, but it could be thousands or whatever. So once we have those words here, we need to compute the score of each word. We need to know like how good the word is. And this is called, in that field, we evaluate the fitness. So it means that we compute really the score of each word. So now we're interested in like whether we have found the solution, whether there is a word that has a score of 3. If we found a word with a score of 3, then it means that we found a solution. Then if not, then we need to, to enter a second iteration. So we need to select some of the words from the initial population here. And then we need to reproduce those selected words. And then here we create a new population, and then we have a second loop here. So very brief. So here, test. Okay. So here, this is, well, the book I'm currently writing here. And if you click here, wow, why? Wow, amazing. Okay, really amazing. Okay, so here this is the one chapter about genetic algorithms. So if I go here, there is a small example here. Cut and paste here. I go here. And so here this is so here gato, which is the Spanish word for. So here I can have words to find as array. What to find here is, so here we are looking for the word cat, and here number of genes is simply the number of letters size. So here I do tuk. And then here we found that the genetic algorithm here is, has found the solution here. So I can look at the traces here. You see that the first iteration, then the best word was CAD, C-A-D, then quickly found cat. Here we can have some more, hello, I love you. And again, here, the blue one here, this is the fitness of the best element at each iteration, each generation. And also here, the green, this is the average, and the red, this is the worth. So something interesting here, the distance between the blue and the red, this gives the diversity that there is in the population. So it's very important that the red to be low and the blue to be high, like to have diversity in the population. So this is just a simple example here, and we found this is the way that it works. Okay, so genetic algorithm is an evolutionary computation techniques that automatically solve problems. And the very cool thing about that is that there is no need to say what the solution should look like. There is no way to say how to get to that solution as you will do in a classical algorithm. In a classical algorithm, you need to specify how to get to that solution. But here, we don't need to say that. We just need to say, oh, if you give me a solution, how good that solution is. And the system will really find the solution for you. And that is really something completely different than the traditional programming here. So generally speaking, genetic algorithms are literally simulation of natural evolution, really. If you take the research papers that describe the algorithm, you will really see that in many, many places, they're really referring to the way that nature is built, the way the chromosomes are formed and the alignment you can have. So really, there is a very strong root from biology. And so genetic algorithm is considered, can be used as an optimization techniques. What does it mean, optimization techniques? It means that if I have f the x equal y, and the genetic algorithm is looking for the x's that makes y very high. And that is really the whole point, looking for the x's in such a that f the x go high. So y here is just a number, like a float number, integer, whatever. In that case, in the one example, it was simply an integer. And the x here, the x could be a tuple for any dimensions, anything. So it's really a tuple that can be very, very multidimensional. I can have like a tuple that belongs in a world of 100 or 1,000 dimensions. So an individual. So an individual, this is an element of population, and each individual has a chromosome informations, and this is composed of genes. So, and here I have an example of individuals, made of colors. So if I want to be, my website, a gene here, this is an index in the chromosome, and the allele, this is the value. So, but just for simplification, I will say this is a gene. And the population, this is a set of individuals. So in the basic algorithm, all the elements, all the individuals, they have the same size. You could have different size, but most of the cases, they have the same size. And so we need the score. So the fitness function is simply a f function that takes here an individual and give a number here. And again, the whole idea of the genetic algorithm is to search for the individuals, to search for those guys here that makes y very high. So I will give you like a couple of examples now that are a bit more researchy bit. So optimizing a server. So imagine here we have the Java virtual machines. The Java virtual machines, this is a complex, highly sophisticated virtual machines. It has like over like 200 options you can give. Whenever you want to run an application, there is 200 options you can give to the JVM to configure the G, to configure the memory, or many things. And for one given applications, according to the options you are giving to the JVM, you may have a different memory consumption, or so you can have a different energy consumptions. So the y here could be, for example, the number of memory used, and the x here could be a set of options to the JVM. And yeah, another example here is with the space. So something I'm very interested in, because at the University of Chile here, we are building satellites, and in next year we will send 3 satellites. And when you have more than one satellite in the space here, then you can talk about a constellation of satellites where they can start to communicate with each other. So we are currently working on that, and more on the software part. And one of the challenges here in making satellites talk each other up there in the space, then you need to face some very harsh conditions. And making satellites talk with each other and talk with the ground here, then you need to deal with all kinds of weird situations that involve some solar tempest and magnetic field or many other fields, many other problems. So something we're currently working on, but NASA has an interest in that particular problems where that involve designing an antenna to make satellites communicate. So here, this is the result of using genetic algorithm to find the antenna used by the satellites. And what here is, so this antenna here, you see that this antenna looks like a paper clip that someone has played with, right? I mean, that there is no, doesn't seem to be a natural solution. And the reason is that this is not human who made it. This is the genetic algorithm. And that antenna, that particular antenna, was really one of the, that was the result, that was the best candidate antenna to maximize the communication between satellites. So again, the idea is very, I mean, the whole way that the genetic algorithm has found it is very simple. So here we have f the x equal y, and the x here is just a list of statements. A list of statements. And a statement could be like, go forward for a given length, or it could be rotate, some rotation about x, y, or zeta. And here the y is something about the communication that involved, in that case, the voltage and impedance, to maximize the communication. So here there is this paper if you want to know more about that. But that's exactly what, this is exactly what I did. So genetic algorithm also used very much in testing, in software testing. So here again, we have the f the x equal y, and the x could be a sequences of actions one can take on an application. So in the Android world, this is very, very common to have those algorithms where an action could be pressing a button, or could be entering a field, or doing a gesture, whatever. And the y here could be, for example, the number of tested functionalities, the coverage of the application. And the idea is that you are using genetic algorithm to maximize something, which is, the number of bugs that are found, which could be, the number of exceptions that are thrown. Or so it could be like useful to find dead code. Imagine that you have your application here, and you are trying to test as much as you can, and your fitness function is the coverage. So the algorithm is trying to increase the coverage of your application, but maybe there are some parts that you cannot cover, and those parts, maybe they are dead code. And also something we are currently working on with Juan Pablo Sandoval from Bolivia is, again, we have the f, the x equal y, and the x here are Smalltalk statements. A Smalltalk statement, really any Smalltalk statement, could be sending a message, creating an object, whatever, which is a Smalltalk statement. And so randomly, we create those Smalltalk statements, and then we measure the fitness of it, and what is the coverage, what is the number of tested functionalities. Something we're currently working on, and thanks to the sponsoring from Lime Research for that. But I think Juan Pablo will show that at some point during this week. And last example that currently working on, so I have one PhD student and one master student working on that problem, where in robotics. So we have actually that robot. This is the value of that robot is 2 Ferraris. This is what it costs. So so here we have. So again, the way that you program a robot, pretty much will be using a state machines. You may have a very complex state machine to express the behavior of that robot. And the thing is, we are using genetic algorithm to measure the robustness of that of that software. And one of the things is the X here will be the set of random inputs that for a robot state. And the Y here would be the number of raised warning or errors. And we build the visualization with, guess what, Russell, where here each box here is a state, and the size of that box is the time spent while executing that state. And the yellow here means that the state has some warnings, and the red has some errors. So we have a couple of papers on that. So, okay, so something I would like to talk a bit more about that, the selection mechanism. So Again, the selection phase is about selecting the elements from the population that deserve to be parents. So there are several ways you can select the parents. So there are the two most popular algorithms are the roulette or the tournament. I won't talk about roulette. It's used a lot, but I won't talk about it because I promise you there won't be any math. But I will talk about the tournament. And the tournament actually is pretty simple. So you take a number of elements from the population, you make them compete. That's all. That's really all. So you can take 5 elements, for example, and you select the best element from these 5 elements. And then you say, okay, that best element here will be used as a parent. And the good thing with the tournament is that this is an algorithm that is highly parallelizable, something we are currently working with Matteo on making genetic algorithm on a cluster of CPUs. And here the reproduction phase. Yeah, so the genetic operation here really comes from, again, Charles Darwin. And if you take the original thesis of Darwin, it says that in order to have natural selection, you need at least 3 ingredients. The first one is heredity. It means that a child should receive some of the properties of the parent, some of the interesting properties. If the rabbits run very fast, then hopefully the baby rabbits will also run fast. Also, you need some variations. It means that you need to have some random mutation that happens in a child DNA. So you cannot, the children cannot be an exact copy of the parents. There has to be some random mutation. If the father and the mother, they have blue eyes, maybe the kid will have green eyes. And also the selection. We need a selection mechanism, but I already talked about that. So I will briefly mention what are the genetic operations used commonly. The first one is the crossover. I don't know if you remember your lectures when you were kids in biology. This is exactly that. So here we have 2 elements here. The crossover works that way. We need a random position here, and then we select 2 parts, and then we compose them. That part here goes here, and that part here goes here. And there is also variation of the crossover where you can, type these 2 parts and these 2 parts here to form two elements. Another genetic operation here is the mutation. So you have an individual, and you are randomly replacing a gene by another one. And that's all. And evaluating the fitness. So genetic algorithm can find solutions to very complex problems, but you do not say what this solution should look like. So what is the magic here? So the fitness often could be complex to define, because you need to be able to evaluate a model that could be extremely complex. So there are several ways you can configure the genetic algorithm: the mutation rate, the population size, the number of genes, and the fitness functions. Some of the benefits of the genetic algorithm. So yeah, there are many benefits. One of them is that genetic algorithm, normally it should not. While running the algorithm, it is not trapped into local minima, local optima. And that is very important. Anyone doing some machine learning, they have to deal with that problems all the time. Like local minima is when the fitness function, for example, will do that or that. Then the genetic algorithm can find something here while the solution is up there. But genetic algorithm does not get trapped on that. And also, genetic algorithm really works with any kind of variable that can be discrete or categorical. It could be numbers, colors, could be strings, whatever, really whatever. If you take, for example, all the deep learning approaches, there has to be numbers all the time. But in genetic algorithm, you don't need numbers. Just to compute the fitness has to be expressed as a number. But that's all. So here an example, you can have direction for robots or characterization of an antenna segment. And also the very cool thing here is that genetic algorithm can be combined with other AI techniques, in particular deep learning. So yeah, I won't talk much about that, but this is fascinating. And to me, this combination of genetic algorithm with deep learning is really what is getting closer to the AI that you can find in science fiction books and movies. This is really, really impressive. This is all this thing where you can find you can create some artificial players playing each other, and yeah. So we do a couple of demos now. Does it make sense? Yeah? So here, again, here, this is an example from the book. So here, the book, so in that chapter here is about, where is it? Yeah. Making robot find an exit in a maze. So here, I run the thing here. And here I have the view. So here I have a robot. So I create a map with some obstacles. And the robot, so what are the genes is to go one step north, south, west, or east. And then the fitness is simply, oh, robot, please follow my orders, given by the genes. And then the fitness will be simply the distance between the robot after having followed the orders with the exit in the map. So the robot has to find the exit. And that's pretty much it. So here we, and also like, here we say that we want the genetic algorithm to really minimize the fitness. So the idea is to find the lowest point in, and here we see that the blue curves here is reaching 0. It means that the robot has found the exit. So what is the exit here? The map is that one here. And here you see that the robot started here, has ended here. Also here, another example here. Wow. And here this is the zoomorphic creatures. Yeah, the zoomorphic creature is kind of cool. So I will not run the algorithm right now because it takes a couple of long minutes. So here this is the idea. Okay, so the idea here is to create a small creature that can learn how to walk. So the creature is made of 10 nodes and 45 muscles. And the muscles can have a length, a strength. You can have also some oscillations here. And yeah, so I randomly create muscles, 45 muscles. And then I make the creature, you know, to use, so I materialize the creature from the genes, which the genes contains the muscle description. And then I just make the robot walk during 3,000 steps. And then the fitness is how far to the right the small creature goes. So, so here we see that the blue one, this is the best element. It means that, yeah, that curve here shows that the creature are able to walk. So here we show the example here. Yeah, yeah. And this is, yeah. And the interesting thing is that creature didn't know at all how to walk, but you know, he learns. If you don't trust me, then here we can see the different steps of the evolution here. So if we go here. So here we can see different creatures. So here the best one is the red. This is really the creature that I take from the genes here that were computed here. Then the second one is the green. So the best one is the red. The second one here is the green. You see that the green here is going a bit, you know, is making tough computation against the red. But ultimately the red here will win. So again, you know, like the yellow one, it was taken at the 50th generation. So at the generation 1 or 2, the creature doesn't know at all what it's supposed to do. But from, you know, like the whole population of elements that are randomly created, some of them will go a bit on the right. So the genetic algorithm will pick those creatures that goes a bit on the right and try to make some improvement by doing some genetic operation between them. And ultimately, generation after generation, and in that case, 128 generations, then is able really to walk on to go fast. So there are some more examples here on the book, you know, like the third part, which is currently under writing, which is about neuroevolution. So here, for example, like yesterday evening, I was working on the Pong game where you can create some random players. At the beginning, you know, the player doesn't understand that he has to, you know, to hit the ball. But if you create plenty of random players, then some of them will understood that they should hit the balls in order to maximize the fitness. And then you can make some tournaments between different players. So this is a part of the book that is coming very soon. So I'm almost done. Yeah, okay. So genetic algorithm can be used to solve some AI problems as soon as those problems can be expressed in terms of optimization. You need to have the f the x equal y. As soon as you have that, then you should be able to use some genetic algorithm. Then genetic algorithm just in the way to say how good the solution is. That's all. There is no, you don't need examples, as you have deep learning, there is no need of examples at all. You just need to say how good the model is. And so why I'm talking about genetic algorithm here? Because it's very simple. It's very simple to learn, very simple to implement. So if you follow that talk, you should be able to implement it on your own. Else you can really have a look at the book. So the book here, Agile Artificial Intelligence, well, currently it is online here, the good news. The bad news is that it is online just until the end of this week. And yeah, because it will be published by iPress, and thanks to Seb for that there. And so yeah, it's just until the end of this week. So if you want to get the thing, then you can just copy it now. So, and again, I really want to thank Lime Research, in my name and the name of my team, because without the support of Lime Research, we will not be here, and probably we won't be working on AI at all. So thank you very much.
Yeah. With genetic programming, but have you tried with, for instance, using bytecodes as genes?
Yeah, indeed, this is about genetic programming. Again, very, very cool ideas. So you remember genetic algorithm? So where each individual has a chromosome-like information. This is a sequence of genes. Okay, this is what we just talked about. Genetic programming is instead of having a sequence, instead of having an ordered collection of genes, then you have a tree. And the cool thing is that the tree could be an AST, could be an abstract syntax tree. So each individual could be a program that you are currently executing. So the genetic programming is really looking for the best program to solve a problem. So you don't need to write your program by hand. Genetic programming can really find the problem for you. So yes, it does work. And surely in the second edition of the book, there will be a chapter on that. So enjoy the coffee break.